Dimensional analysis shows the relationship between the physical quantity and units of measurement. In the previous video, we talked about dimensions of various physical quantity, and I explained that dimension shows relationship between physical quantities. In this video, we're talking about dimensional analysis, how to solve questions, problems on dimensional analysis, and also see the application and the limitations of dimensional analysis. First, let's talk about the application of dimensional analysis. How can we apply dimensional analysis? Basically, dimensional analysis tells us the relationship between physical quantities. It also tells us the consistency of a dimensional equation. What I mean by this is how correct a dimensional equation is. This is a principle called the principle of homogeneity. What this simply states, don't mind the fancy word, what this principle simply states is that for a dimensional equation to be consistent or to be correct, the left-hand side of the equation must be equal to the right-hand side of the equation. Let me show my lights. Let's take a look at a very popular equation. Let's use V equals to U plus AT, one of the equations of motion. So let's see if this equation obeys the principles of homogeneity, which means that let's see if the dimensional equation is consistent or true. For it to be consistent or true, it means that the left-hand side, which is this V, the dimension of the left-hand side must be equal to the dimension of the right-hand side, which is everything you see over here. In case you don't know how to get dimensions, you can check out the previous videos to understand the concept of dimension. The dimension for velocity, don't forget velocity, the definition for velocity, and put that over here. Velocity is displacement over time. So hence the dimension will be equals to displacement is L and time is T. So this will give me LT raised by minus 1. Don't be confused. Sometimes you can write this as, don't forget dimensions I told you about. I gave you 3 major dimensions, M, L, and T. Okay, so since there is no M in this dimension, you can just write this as M raised by 0, but it's T equals to 1. So this is 0 raised by 0. LT raised by minus 1. This and this are correct. They are the same. Okay, some textbooks might write it this way, or some options you might see it this way instead of in this format. So M raised by 0 simply means 1, which is the same as this over here. So the dimension of velocity is M. Let me just use it that way. M raised by 0, LT raised by minus 1. Okay, this equals to U also represents velocity. That means it's the same thing. M raised by 0, LT raised by minus 1, plus what's the dimension for acceleration? I advise you to pause this video and calculate for the dimension of acceleration. Okay, this over here is the dimension for acceleration. So let's plug that into here. So what do we have? We have M, sorry, let me change the color. We have M raised by 0, LT raised by minus 2, that's for acceleration, times for T means time. Dimension for time is also T, so T raised by 1. So if I simplify the left-hand side, I'm going to have M, or right-hand side rather, we're going to have M raised by 0, LT raised by minus 1, plus M raised by 0. Now here we have L. Okay, here we have T raised by minus 2 and T raised by 1. That will give me T raised by minus 2 plus 1, following the principles of indices. So that will give me raised by what? T raised by minus 1. Okay, in dimension, whenever you add dimensions that are the same, it's equal to the same thing. That means that this, since these two are the same, this and this is equal, they're the same. When you add them together, it won't give you, don't do it like algebra, where you say this plus equals to no. It's going to give you the same thing, which is what? M raised by 0, L T raised by minus 1. Do you understand? And what is the left-hand side? We still have this, which is M raised by 0, L T raised by minus 1. And what do you notice? You can see that the left-hand side is equal to the right-hand side. That's what I mean by consistency. So Dimensional analysis tells us, okay, if a dimensional equation is consistent, following the principles of what? Of homogeneity. So this equation, V equals to U plus AT, it obeys the principles of homogeneity. One last function of or application of dimensional analysis is it helps us to convert. It has one of the very major functions, okay, or applications. Convert one unit to another. So it helps us convert one unit to another. For the purpose of this video, we're going to be dwelling majorly on calculations and not conversion. Maybe in other videos, okay, I'll make a video to explain the conversion of units from one form to another. So, but in this video, I'm going to be dwelling on major calculations on dimensional analysis. Now we've talked about the application. Let's talk about the limitations of dimensional analysis. So as we've learned already now that dimensional analysis have applications, okay? But it still has some limitations. One of the major limitations is that dimensional analysis does not give us enough information about a constant. So how will I put that? Doesn't give information about constants. So we don't really get enough information about constants, okay? Don't worry, in calculations, you learn more about that, okay? Learn more about that in the calculations. So we cannot derive the dimensional analysis or the dimension of some functions. Functions like this, we call this a logarithmic function. Functions like this, we call this an exponential function. Functions like this, we call this a trigonometric function. So these functions, you can't derive the dimension. And lastly, with dimensional analysis, we cannot know if a quantity, a physical quantity, is scalar or vector. We cannot determine if a physical quantity is scalar or vector. So these are the limitations of dimensional analysis. When we start solving questions now, I think everything will start to get clear. This question was picked from Adewale Physics for students of Unilag, okay? So I just found the question, I decided to jump into it. I know it's not very clear, but let's just try to train our eyes. The question says, experiment shows that the frictional drag force, F, so this F here is frictional force, okay, of a car moving in the air depends on the velocity V. So V is velocity. Let's note these quantities of its motion. Density, rho is density, okay? We are given density of air through which it travels and the cross-sectional area of the car. That means A is cross-sectional area of the car, okay? So if the force F, okay, let's write that out. Said F equals Kp raised by x, V raised by 2y, and A raised by z. Don't forget what the quantities represent. F is force. This P here is not actually B. I just wrote that P is rho, which is density. V is velocity, and A is area. So where x, y, z are integers and k is dimensionless. Don't forget I said that's one of the limitations of dimensional analysis. We don't really give much information about the k. So k is dimensionless. That means forget about k. We don't have any business with k. That would be it, okay? So find the value of x, y, and z. Let's find the values of x, y, and z. Very simple. Trust me, very, very simple. Just take your time, and if you need to watch this video 2 times, watch it 2 times. No problem. So let's start with the first one first. What is the dimension for force? Let's do that over here. Okay. If you were in the previous videos, I think this will be easy for you. We know that force is mass times acceleration. Okay. Mass is m. That's the dimension for mass is m. Dimension for acceleration is LT raised by minus 2. We did that up there. So this is dimension for what? For force. Let's go ahead and find the dimension for the other quantities we have here, which is density, okay? And density is mass over volume. Dimension for mass is m. dimension for volume is L raised power 3 because length times breadth times height. This is going to give me ml raised power minus 3. If you decide to add your t, just add t raised power 0. You understand? Since there's no t here, so t raised power 0 is obviously 1. The other quantity we have here is velocity. Velocity, I don't think I don't need to. Okay, let me just write it out. Displacement over time. So the dimension for displacement is L, for time is t, so we're going to be having Lt raised power minus 1. Again, if you want to add your m, just add m raised power 0. It's not very, very useful, but in good practice, you can just add that. The next quantity we have is area. So area is length times breadth. So that is dimension will be L times L. So breadth is also length. So it's going to give me L raised power 2. So let's put all this into the equation, okay? So for F, what do we have? F is m Lt raised power minus 2 equals to, we have our K. Rho, which is density. Density is ml raised power minus 3 t raised power 0. Now, if you look at density, now density is carrying the power of x. So what do? Let's put this in a bracket, raised power x. All right. Next quantity we have velocity, which is m raised power 0, lt raised power minus 1. And also, v is carrying raised power 2y. So this is going to give me raised power what? Raised power 2y. Lastly, we have a, and a is L raised power 2. Don't forget, we can also write this here as m raised power 0, L raised power 2, t raised power 0. I think you get the idea. This is 1, this is also 1. So we have m raised power 0, L raised power 2, and t raised power 0. This is not very, very useful anyway, but in good practice, you can learn to solve this way. This all raised power what? Z. So let's open the brackets and use the power to multiply the other powers in the bracket. So here we have m Lt raised power minus 2 equal to k. X here will multiply the power of m, so it become m raised power x, right? X times minus 3 will give me L raised power minus 3x, okay? And this will give me t raised power 0 because x times 0 is still 0. I think that's clear. Then we have, in the second part, we have 2y, we multiply 0 to become 0. So we're still going to have m raised power 0, L raised power, now we have an invincible 1 here. So 2y times 1 will still give me what? 2y. Then t raised power minus 1 times 2y will give me minus 2y. Next, we have this. Z multiply everything just like what we did here. So 0 times z is going to give me m raised power 0, not change. Okay. L raised power 2 times z. 2 times z will give me 2z. So this is going to give me L raised power 2z and t raised power 0. Simplifying the right-hand side, we have k. Now, what we can do here is principle of indices. Now, we have times in between. We have times here. We have times here. Okay? So we can bring those ones that have the same base together. So what are we going to have? Let me create space. What are we going to have now? We're going to have m raised power. Let's bring all the m's together. We're going to have m raised power x times m raised power 0. That's times m raised power, m raised power 0 times, also we have m raised power 0 by here, m raised power 0. So that's that for m. Let's look at L. For L, what do we have? We have L raised power minus 3x. That's what we have over here. Where else do we have L? We have L over here. So that's times L raised power 2y. Where else do we have L? We have L over here, which is what? L raised power 2z. Moving on, the last one we have here is t. This is going to give me t raised power, what do we have here? 0 times, where do we have t again? We have t over here, which is t raised power minus 2y times t raised power 0, which is what we have over here. So simplify. Don't forget that k is dimensionless, so we can just cancel that out without any business with it. So simplifying your indices here, we're going to have m raised power x plus 0 plus, don't forget that times becomes what? Plus. So x times x plus 0 is going to give me x. So m raised power x. Let me match the color. M raised power x. Okay. Times, what do we have here? We have L raised power minus 3x. This becomes plus 2y and plus 2z. That's principles of indices here. Then for the last one, we have times t raised power 0 minus 2y plus 0 is going to give me minus 2y. Don't forget that we still have the left-hand side. The left-hand side is m l t raised power minus 2. That's what we have in the left-hand side. Let's put this down. Now, what can we do? From this point, we can simply compare the coefficients and simply compare coefficients. If you look at m, you have m, you have l, you have l, you have t, you have t, and compare their coefficients. M here is carrying an invisible, let me use a red color. It's carrying 1 raised power 1. So if you compare m raised power 1 and bring that out, m raised power 1 equals to m raised power x. So if m cancel m, what do you have? X equals 1. Very simple. Let's look at L. Okay, or let's look at t. I think looking at t is easier. Let's look at t. For t, what do we have? T raised power minus 2, that's on the left hand side, is equals to t raised power minus 2y on the right hand side. So if this cancels this, we have minus 2 equals minus 2y. Dividing both sides by minus 2, we're going to have our y to be equals to, this cancels this, we have 1. So our y is equals to 1. So let's deal with L now. L on the right hand side, we have L raised power 1 equals to, on the left hand side, we have L raised power minus 3x plus 2y plus 2z. Again, L cancel L. What do we have now? 1 equals to minus 3x plus 2y plus 2z. Now we know what our x is. X is 1 and y is also what? 1. So what do we have? 1 equals to minus 3 times x is 1 plus 2 times y is also 1 plus 2z. You know what z is yet. It's going to give me 1 equals to minus 3 times 1 will give me minus 3 plus 2 times 1 will give me 2, then plus 2z. I hope you're following. This is going to give me 1 equals to minus 3 plus 2 should be minus 1, then plus 2z. So take this over here. We are going to have 1 plus 1 equals to 2z. So therefore, 2 equals to 2z because 1 plus 1 is going to give me 2. So divide both sides by 2. Z will be equals to 1. So let me bring that over here as a summary. So now we know that x is 1, y is 1, and z is also 1.